today we're going to talk about the difference between when momentum is conserved in a system and when mechanical energy is conserved in the same system. First, let's deal with momentum. Momentum is conserved when a system is isolated. How do we know when a system is isolated? When the net force on that system, which is a vector, is equal to 0. Why is this true? Well, because the net force on a system is equal to the rate of change of its momentum. Both of those quantities, net force and rate of change of momentum, are vectors. And when they're both 0, that is, when the net force is 0, then the rate of change of momentum is 0, and therefore the change in momentum of the system is 0. And that is the same thing as saying that the initial momentum is equal to the final momentum. Now let's talk about mechanical energy. When is mechanical energy conserved? Well, we know in general that the change in the internal energy of the system plus the change in the mechanical energy of the system is equal to 0. If it's also true that the change in the internal energy of the system is 0, then it will be true that the change in the mechanical energy is 0. So we want to ask ourselves two questions when dealing with any system. One, is the net force equal to 0? If that's true, then the change in momentum is equal to 0, and momentum is conserved. Two, we want to ask ourselves if there's any reason why there would be a change in internal energy in the system. If there is, then there must be a change in mechanical energy to compensate for that, because overall energy does not change, and therefore in that case mechanical energy is not conserved. So our first example is going to be the example of free fall. It's a fairly simple example. We have a mass m. We make a free body diagram for that mass m. The only force being exerted on that mass is the force of gravity. We define a coordinate system such that up is positive, down is negative. The net force on that system is negative Fg, and that's equal to the rate of change of momentum, and that's not equal to 0. So we have the result that the rate of change of momentum is equal to negative mg. So in other words, momentum is changing with time, but specifically it's decreasing, or in this case becoming more negative with time. And that is not equal to 0. In other words, for this situation, because there's a net force, you have that the rate of change of momentum is not equal to 0, and therefore momentum is not conserved. What about mechanical energy? Well, let's write out our equation. Delta internal energy plus delta mechanical energy is equal to the change in total energy, which we know is 0. And now we have to ask ourselves, is there any reason why our delta I would be non-zero? I would say that based on experience, we know that our delta I is 0 when the only force involved is gravity. And this is true because gravity is conservative, but it also should be true based on some level of sense that the internal energy of an object neither increases nor decreases when gravity is the only force involved. So therefore, the change in internal energy is 0, So therefore, delta ME is 0, which means that ME initial is equal to ME final. So over here in free fall, we can say that P initial is not equal to P final. And remember, these momentum values are vectors, but on the other hand, all this motion is in one dimension. And we can say that mechanical energy initial is equal to mechanical energy final. And again, the first one is not conserved because the net force is not equal to 0. The second one is conserved because the change in the internal energy is equal to 0. Now let's just quickly talk about a car crash. In a car crash, there are many irreversible things happening in the interaction. The deformation of the cars, for example, that is not a reversible process. And there should be an intuitive sense that gains or losses in internal energy equate to something irreversible happening. And because some things that are irreversible are happening, delta I is not equal to 0. So therefore, in the equation delta I plus delta ME is equal to 0, we have delta ME not being equal to 0. In fact, in the course of the car crash, the internal energy increases. And because that sum has to be equal to 0, mechanical energy decreases. So in other words, mechanical energy initial is not equal to mechanical energy final for the car crash because there's irreversibility in that interaction, and therefore the internal energy changes. The momentum, however, in the direction of the car crash is conserved as long as when the two cars collide, they transfer momentum in the direction of the interaction with each other, but not also with anything else. In that case, the system can be considered isolated along the direction of the interaction, and momentum initial is equal to momentum final because the net force is equal to 0. So this applies to the car crash, and this applies to free fall. Our last model is the elastic collision. As long as two objects which are colliding elastically are transferring momentum between each other, but not also with anything else in the direction of the collision, then that system is considered isolated. So again, the net force is equal to 0, which is equal to the rate of change of momentum. So therefore, P initial is equal to P final. So momentum is conserved. Also, there are no irreversibilities in an elastic collision. You get back all of the kinetic energy that you lose because there's no irreversibilities. Because there's no irreversibilities, there's no change in internal energy. So you now have that delta ME is equal to 0 because delta I is equal to 0. In other words, in an elastic collision, both momentum and mechanical energy are conserved. Momentum is conserved because the system is functionally isolated. Mechanical energy is conserved because everything's reversible, so there's no change in internal energy. That contrasts with the car crash, where momentum is still conserved in the direction of the collision, As long as that collision is functionally isolated, there's no net force on the two cars. They transfer momentum between each other, but not also with anything else. However, there are irreversibilities in the system. Deformation, for one. And those irreversibilities result in loss of internal energy. Gain of internal energy, and therefore loss of mechanical energy. Anytime there's a delta internal energy, there's also a delta mechanical energy, such that the sum of those two is zero, and that is the case in the car crash. Finally, going back up to free fall, the object falling is not functionally isolated because there is a net force on it. Therefore, there is a rate of change of momentum. Therefore, momentum is not conserved. However, there are no irreversibilities because the type of interaction involved is a conservative one, and therefore mechanical energy is conserved. So you can see, based upon these three examples, that mechanical energy conservation and momentum conservation are independent, and one can be conserved without the other being conserved. Here, momentum is not conserved, mechanical energy is. Here, momentum is conserved, mechanical energy is not. And here, both are conserved.